So I hope that those two videos gave you a sense of the technology involved and the massive scale involved. And first, let's look at the size involved. These things are enormous. So if you take the tower height of 260 feet and you put a blade of 150 feet on top of it, those things are topping out at 410 feet in the air. That is a long way up. And you're going to see that wind turbines continue to get taller because as they get taller, they can increase the blade size. And if you increase the blade size, then you can increase the generator and you can develop higher powered systems. In fact, in offshore wind, there are some enormous towers going up or towers planned like 500 feet tall. But the weight of those things is immense. And I pulled up a very popular 2 megawatt Gamesa system, very popular wind system, and I researched its weights. And you can see that up on between the hub and the blades and just the generator sitting atop, that's like over 230,000 pounds that you have to hang on to. And then the tower itself is another 440,000 pounds. It gives you a sense of why they have to pour so much concrete and build that pad out and drive it down, because it's hanging on to a whole lot of weight, which incidentally says that if these things ever are decommissioned and replaced, the environmental cleanup is not exactly going to be insignificant, because it took a lot of concrete in the ground to make that thing viable. So they are enormous in size. And if you've ever been up close to one, you quickly feel very small. It's important to understand the technical specifications because it helps us as business people get a sense of what's going to be required to make this thing go. I think I've mentioned to you that a million years ago, my undergraduate degree is in aeronautical engineering, and you all know that I still fly airplanes. And so I marvel at the very state-of-the-art windfoil technology they've got in terms of twists and trailing edge twists and things like that. So I think the thing to keep in mind is you're not going to see breakthroughs in the aerodynamics of wind turbines. In other words, they're not going to get suddenly more efficient because they make better blades. The blades today are state of the art, and the advances in aeronautics, for the most part, were done 30, 40 years ago. They were complete. The improvements that you're getting are very small, very incremental improvements. So I'm amazed at how they've incorporated truly leading edge technology, no pun intended, into the design of the airfoils. But notice that one of the things that is a key technical perspective is as the wind comes in on this side into the turbine, it exits out the back end slower. Now, the greater the difference between the entry and the exit speed, the more energy that the turbine has absorbed. So that's good, but that has real ramifications for how you sight wind turbines. And so I found this very rough rule of thumb, and it is a very rough rule of thumb for reasons that I'll explain in just a second, that they typically dedicate about 50 acres per one tower. So if you have a square of land of 640 acres, then in theory you could have 12, 13 turbines in that 1 mile section. In reality, probably it's not going to be nearly that dense because wind speeds dictate the layout. Because you don't want the energy absorbed, and you don't want to be building turbines in the downwind of other turbines because the energy has been absorbed. The wind speeds are important. You try to figure out the predominant direction for the wind speed and then build the wind turbines perpendicular to that predominant, I shouldn't say speed, I should say direction, that predominant wind direction. And if I could take you flying in my little airplane and we'd fly over some of the wind farms, you can see very clearly where they think the wind predominantly blows from, because you would see the layout, and it would make sense to you that they don't put turbines behind other turbines, or at least not closely behind. They'll let them be much further behind them. So it takes a lot of terrain to build a wind farm. The more variable the wind direction, the further apart you're going to have to space the towers. If you have a very strong and very predictable wind, for example, along a ridge line, then you may just be able to build towers relatively closely spaced right across the top of that ridge line. Speaking of wind speed, though, I keep talking about speed when I meant direction. The winds have to be blowing, not surprisingly, a certain amount to even allow the wind turbines spin fast enough to generate electricity. So I looked up the specifications for a GE 1.6 megawatt system, and I'm reading from a table, or I'm sorry, reading from a graph, so these are by no means exact. But the minimum speed is called the cut-in speed. Wind speeds below that won't spin the turbine fast enough to generate electricity. For the GE system, about 8 miles an hour. It then scales up almost linearly to its full generation speed. And for the GE, it was about 25 miles an hour. Between 25 and its safety limit, and I really couldn't find a good number, so I did see some numbers around 56 to 60 miles per hour. At that wind speed, it just kind of generates flat because the turbine only can spin so fast, and so they're changing the blade angles to make sure that the turbine doesn't spin too fast. And then when it gets above that wind speed, what they do is they feather the blades, they turn them perpendicular to the wind, and they lock the hub because it's spinning so fast the system can't handle that. Because of that, you never assume that a turbine is going to produce its spec capability. The most common capacity factor you're going to see as a rule of thumb is about 40%. You'll see a few percent above this, a few percent below that. But that depends on, that 40% factor is based on experience in the real world. And so obviously when you're siting a wind turbine in a spot where the wind is good, you're going to get close to that capacity factor. If you're siting a wind turbine where the wind is pretty marginal, you might not get even near that 40%. But here's what it looks like. Let's go back to that Gamesa 2.0 wind turbine. So a 2.0 megawatt wind turbine times 8,760, which is the number of hours in a year. So that's megawatt hours times 40%, that's the capacity factor, says that it generates about 7,000 megawatts hours in a year. Well, what does that translate to? These are a lot of internet-based conversions, so I wouldn't consider these necessarily all that precise. But one conversion factor I led, when you do all the math, a 2 megawatt turbine could power about 265 homes a year. Again, I wouldn't put a high confidence in that number, but that gives you a sense of what we're talking about. So many of you live in subdivisions with 250 homes or so you know that one wind turbine could generate enough electricity to power your home for a year. Now, we know that it doesn't generate the electricity at the right times, but that's just a total capacity. In the next video, we're going to talk about where is that wind capacity in the United States.